So this next section, we're now going to talk about what's involved in actually establishing a connection between two TCP peers and what's going on in the background, sort of under the hood in your laptop or in the server to get these connections going. So we're going to talk about some terms you might not have heard about before, like TCBs, transmission control blocks, and sockets, and the three-way handshake. So we're going to go into all those details. So let's just jump in head first. So the three-way handshake. I've alluded to this previously in the previous video that before any data can be exchanged, a handshake process has to happen between the two TCP hosts. And that's what we call the three-way handshake. What's kind of interesting, and we'll see this here in just a little bit, is that sometimes this can actually end up being a four-way handshake if they both try to talk to each other at the same time. Doesn't happen a lot, but that's a possibility. So this is the process of opening a TCP connection, and the main objectives of the handshake, as I've mentioned, is number one, prove that the other guy's there, that he's actually alive and can hear me. And also, let's just take a step back here for a second. We're not necessarily saying that prove that that server actually exists. It's actually two things. Number one, I want to prove that the device itself is alive, that's not like the power cord pulled out and it's dead or something. But if I'm communicating to a server, not only does that server actually have to physically be there, actually have an IP address, actually be plugged into the network, but in addition to that, the server has to be listening on the appropriate port. For example, if I've got a server that's got, the Apache web service running, so this server is expecting to be a web server, that means that when I send a TCP segment to him, he's listening on port 80, or he's listening on port 443 for like secure HTTP. But if I send a telnet packet to that server, he's still there, he's got an IP address, he's physically connected to the network, but he's not listening to telnet. Port 80, he's going to say, what's that? I don't even know what that corresponds to. I'm not listening for that. So that's part of the objective of the three-way handshake. Make sure the device is there and make sure he's listening to this particular protocol that I want to use with him. Then we also do the initial sequence number synchronization. So I tell you, when I establish with you, I say, okay, when I start sending data to you, here's the sequence number I want to start out with. And similarly, when you talk back to him, you say, okay, thank you for telling me that, Keith. By the way, when I'm sending data to you, Keith, here's the sequence number I'm going to use in this direction. So we're talking about a bi-directional communication here, and each direction is using a different set of sequence numbers as they transmit stuff back and forth. And then we also have an exchange of parameters that's needed in TCP. So let's talk about the TCB, the transmission control block. So as it mentions here, a transmission control block, this is basically a sort of an under-the-hood sort of engineering term. It's a block of memory allocated by the central processing unit, the CPU, to maintain state information for a single TCP session. Whoa, okay, let's back up here for a second. Just based on what I've already talked about so far in the first couple of videos, you're starting to get the idea that a single TCP connection, let's just say between your laptop and one web server. Okay, now keep in mind, your laptop has got lots of TCP sessions going on at one time. You've probably got 5 or 6 web browsing windows open. So that's a minimum of 5 or 6 web servers you've got TCP connections going to. You got another TCP connection going to your email server, probably another one going to your instant messaging. You could have dozens of TCP connections open that you're not even aware of. And each one of them has to maintain all of this information. Like when I open up a connection to a web server like INE.com, for that one connection, I have to maintain information about, okay, what's the last sequence number I sent to him? What's the last one he acknowledged back? How much data have I sent to him that he has not acknowledged yet? How much data is in my queue right now, is in my buffer that's waiting to be sent to him? When I sent a frame, there's a timer counting down. Has it expired yet? All this stuff, all this what's called state information is maintained by a single transmission control block. So if I've got 6 TCP sessions open, I've got a minimum of 6 transmission control blocks allocated to keep track of each one of these things. So the transmission control block, when it's created, one of the many things that it's created with is something called socket information. So let's talk about what a socket is, and I'll just whiteboard this. It's actually not that complex. So a TCP socket. So let's say the client is my laptop, and my IP address is that, and the server is INE.com, and his IP address is this. Okay, so I go into my browser and I type, HTTP INE.com. So at that moment, the CPU says, I need to create a transmission control block to keep track of this new TCP connection. I'll just draw that right here as a big block. And this is a section of memory. So this is my TCB for TCP. He says, okay, so what's going to differentiate this transmission control block from the other ones that I've got, going to like Google.com and Outlook.com and everything else? Well, one of the things that's going to make this a unique identifier is something called the socket. And so the socket's going to be 4 pieces of information: the source IP, the source TCP port, the destination IP, and the destination TCP port. So this stuff, all 4 of these pieces of information, is what the transmission control block considers to be a socket. Now let's think about this here for a second. My client is initiating this connection. So I'm going to be the very first one to send out a TCP message. And as we get here just a little bit further, I'm sure you guys are probably thinking, wait, Keith, that's called the TCP sync, right? That's right, that's the TCP sync. So as part of doing this, let's think about how is this information populated? Well, the source IP, that's pretty easy, right? My laptop already knows his source IP. He probably got it from DHCP, or unlikely, but he could have a static IP address. Destination IP. Well, he learned that most likely via DNS, right? When I brought up my web browser, I typed in INE.com, a DNS resolution had to happen, and he learned what the IP address was, and that's how he filled in the destination IP. Now, the TCP source port on my client is something called an ephemeral port. I'll put that right here. An ephemeral port. So an ephemeral port, and we're going to look at this here in just a second, it's sort of like a random port number that's come up just for this particular conversation. And I think in another slide or two I'm going to come up with, I'm going to say sort of like what the range is. What's kind of frustrating about this is that there's different ranges. There's a range that the Internet Assigned Numbers Authority said, we recommend you use this range. And then there's another range that Microsoft says, well, I think we're going to use this range. But it's a range of port numbers that's not assigned to any particular application. It's just it's like a first come, first serve. And so we're just going to pick a port from this range and use that as our source port in this case. And then in this particular case, because I'm doing web browsing, destination port number, probably going to be something like 443 for secure HTTP, right? Or maybe port 80 for normal HTTP. So my laptop here, it's able to fill in this socket. Now the server, what about its transmission control block? Because it also needs one to maintain the state. Before I go into the details of how that's created, let's go back to the slides because I want to catch up a little bit here. But we will get back to this because this is a little bit different. So the creation of a transmission control block can happen in one of 2 ways. One's called an active open. The other is called a passive open. So let's look at each one of these. The active open. That's like what I just drew on my whiteboard. That's typically what the client does. The client says, okay, I realize that I need to talk to this server. So my CPU is going to create a transmission control block from scratch. I'm going to populate it with the socket information that I just learned via DHCP and DNS and stuff. And then I'm going to actively send out a message saying, hey, I want to talk to you. So that's called an active open. As it says here, the transmission control block is not created until the application requests the services of TCP. Because let's think about your laptop for a second. Your laptop has lots of different applications in it that could potentially use TCP. If you really thought about it, there's probably dozens of applications that just come standard, pre-packaged with Microsoft Windows that can interact with TCP. Not to mention all the potential ones you could download from various locations and stuff. So it's not really practical for your CPU. Let's say you boot up your laptop. What if the CPU said, okay, let me look around here. What are all the applications I have? They're not running right now, but what are all the ones I've got potentially that could ask for TCP? Let me create a transmission control block for each one of them. And yet in reality, over the course of the next several hours, maybe only 4 of those applications will actually need to use TCP. So it would be kind of a waste of resources for your CPU to create all these transmission control blocks for stuff that might or might not happen. So on your client, the transmission control block is not going to happen until an application says, I need it. Okay? And then at that point, like I mentioned, the client is going to predetermine the elements required for that socket. And we talked about what that socket is. And then the transmission control block is going to be created utilizing that socket information. ISN in this particular case stands for initial sequence number. So TCP is going to think about, okay, when I first get going here, I need to come up with a sequence number I'm going to start with. Now, when you first learn about TCP from like a CCNA perspective and stuff, usually to make it simple, they just put in the sequence number of 1. In reality, that's not what happens. The initial sequence number is actually a random number. It's totally randomized, and they actually do that to prevent TCP attacks of various natures. And it's a really big number because the actual field that stores the sequence number is a huge field. As I think as we go along here, I think we're going to see it's like a 32-bit field. So your initial sequence number could be some monstrously huge number like 85,212. That's your very first initial sequence number. So there's no way you can really predict what that initial sequence number will be, but it will be stored in that transmission control block as it's created. And now that all that stuff is there, boom, you send your first TCP message, which is the TCP sync message. So that's the client. He's actively creating the open message. Now let's shift our focus over for a second to the server. Now if I implement a TCP server, chances are that server is created and installed with some programs that are up and running all the time, right? Like when I turn on my server, I'm going to want it to instantly be running the Apache web server program or the whatever your email program is or something. So as opposed to a client that could have any number of TCP applications that might need to use TCP and even stuff you haven't even downloaded yet, the server on the other hand is going to say, okay, well, I'm designed for a particular task. So the server's going to say, as soon as it boots up, even though nobody needs me right now, I'm going to create a transmission control block in advance because I'm going to be expecting people to try to communicate with me. I'm not going to initiate the connection. Somebody else is probably going to initiate it. But if they initiate it with me, I have to have a TCP transmission control block ready and waiting to respond to them. So the TCP server will create the TCP in advance to allow the capability of listening for any incoming requests. Now, how does it do this? When we talked about the client, populating the transmission control block was pretty simple, right? He put in his IP address, he put in the IP address of the destination that he had learned via DNS or something, put in his ephemeral port as the source port, put in the destination port of HTTP or Telnet or whatever it was he wanted. Well, what about the server? So imagine, I'm a server here for a second. Nobody's talking to me yet. Well, if I'm going to create a transmission control block, I got to put a socket in there, that 4-part thing. Okay, well, I know what my IP address is. Got that. And I'm creating this transmission control block because I'm expecting incoming HTTP. Okay, so I can put then a port number of 80. I'm listening to that. But what about the other two fields? I don't know who's going to talk to me. So I don't know in advance what the IP address is or what the port number is that they're going to select. So this is called implementing partial socket information. In other words, a passive open means I create a transmission control block and the TCP socket is only partially filled. Actually, in the RFCs and stuff, they'll call this something called an unspecified passive open. Unspecified passive open. So that's basically a partially created transmission control block that's ready and listening. And then what typically happens is, a lot of times these servers will create several of these. Like if you're a web server, for example, you say, well, there's a pretty good likelihood that 25 or 50 people might all try to connect to me within a very short amount of time. So a lot of times the way these servers will work is they'll create a whole slew of these partially open transmission control blocks, these unspecified passive open transmission. So they're all waiting. So when John initiates a connection, they'll say, okay, I'll use transmission control block number 1 that was already sitting there to talk to John. Now I know what John's IP address is. Now I know what the ephemeral port is that John's using. I can populate that, and now this block will be used for all the timers and everything to talk to John. Oh, here comes Sally a few microseconds later. Woo! Got another transmission control block ready and waiting. Now I'll populate with Sally's information. I'll start talking to her. So that's what a passive open is. So this concept of open is really the idea of opening a transmission control block, creating the structure of memory that can be used to store all our TCP parameters. Active means I'm creating this right now because I need to use it right now. I need to actively talk to somebody. Passive open means I'm creating a transmission control block in advance, expecting that someone's going to need to talk to me. So that's the difference between a passive and an active open. So let's go into a little bit more details of these. All right, so setting up a three-way handshake here. So we'll start with that. So at the beginning, the receiver, so we're assuming that that's your server, he creates a passive open, right? He creates that transmission control block in advance, listening for incoming requests. Now your laptop, the sender, your web browsing application tells your CPU, hey, create a transmission control block for me. I need to get going. So that is an active open happening. TCP now gets invoked. TCP can use the services of this transmission control block. It looks in there and it says, okay, I see in there the source and destination TCP port number. I see the initial sequence number I need to use. And so it creates a TCP segment, which is basically just the TCP header. There's no data yet, just the TCP header, and it sends that out. Now in that TCP header, a single bit, a single flag is set called the sync flag, called I'm synchronizing with you. We're going to talk more about that in detail just coming up. So I'm starting to, he says, I would like to synchronize with you, server. Let's synchronize and talk to each other. Now the receiver gets that. He receives the sync. Now in this particular case, this X right here is my initial sequence number. And remember, that could be some huge number like 99,101. We have no idea what it's going to be. It's just going to be some random number. So let's say it's 99,101. So out it goes. So when the server gets that, he says, okay, I know what sequence number he's starting out with when he's talking to me. He says, now what I'm going to do is I'm going to generate my own sync and send it out. He says, I'm going to generate my own random sequence number. Maybe this is 55,200 as his initial sequence number. Now notice what he's doing. In addition to the sync, which is just one bit, the sync flag, which is set to a 1, he also then populates the ACK flag, sets that bit, and in the acknowledgement field, he says the number he sends back is going to be, let's just put this right here, 99,102. Now we're going to go into a little bit more details. Some of you might be saying, well, wait a second. He received 99,101. Wouldn't he acknowledge that? Wouldn't he say, hey, I got your 99,101? Why is he saying 99,102? He hasn't gotten that yet. We'll talk about that. We'll get in there. But the acknowledgement is basically one more than whatever the sequence number was. Okay, well, we'll talk more about that coming up. So now that they've got their initial sequence numbers, the sync has gone out, and this is called a sync plus ACK. That's the second part. And then the last part of this is going to be our final ACK. Because remember, when you send somebody a sync, they need to acknowledge that. So when the server sent his own sync, my client, my laptop, he had to acknowledge that. So that's our three-way handshake right there. And in addition to this propagation of sequence numbers, so we now know what's going on there, we also exchange several other parameters like, okay, what's the biggest segment you can ever send me? Or what's the most amount of bytes you can send me that I can hold on to at one time? And a whole variety of other stuff as well. That's all negotiated during this TCP three-way handshake. So this is your typical setting up of your connection. One person will be the active side, one person will be the passive side. And you now know how the transmission control blocks are created based on whether you're active or passive. So this is a three-way handshake. Sometimes, not very often, but sometimes two devices will try to talk to each other at the same time. Like maybe this is a peer-to-peer type application or something. So now they're both creating active open. So maybe you've got two laptops that are trying to do some, they're connected over the exact same hub or switch, and they're trying to do some, multiplayer game or something. Who knows what's going on here? But they're basically trying to set up the connection at the same time. So what do? They both come up with their own individual sequence numbers. They're not going to match. I mean, the chance of these numbers matching is infinitesimal. So they're going to be different. They're going to send syncs to each other. And when you send a sync, what do you expect? You expect an ACK back. So sync, ACK. So in this particular case, what are we not seeing? We're not seeing that one message that's called a sync plus ACK. So in the previous diagram, the receiver, the server said, oh, you want to talk to me? Okay, I need to synchronize with you, and I'll acknowledge your sync with me. That was the sync plus ACK, all contained in one packet, in one segment. Here we're just sending an exchange of syncs and then an exchange of ACKs. So what we're really kind of looking at here is a four-way handshake. Like I said, doesn't happen a lot, but it's possible that you might see this.